simple form of Cauchy's theorem and Cauchy's integral formula and so on that are needed for this power series expansion, we'll do in the beginning. Now once we get that, we can have a lot of things. We can derive many things, all of which are basic properties of analytic functions. And then the more general form of Cauchy's theorem and so on, other topics, we'll come back to them afterwards, right? After we get some of these basic things. So we'll follow a kind of thread initially, and then we can take other paths, right? We'll just follow a path which takes us to some of the most basic things in complex analysis, and then we can go to take other bylanes. Of course, the topics are all standard, so whatever books that we follow, the approaches may be slightly different from book to book, but the basic material is all the same. So it's fine. I'm not going to follow any particular book or anything. So should be okay for anyone as far as the subject goes, Alphos or Conway or whatever. But the things may not be exactly as given in Alphos or Conway or anything. But the things are the same anyway, right? The basic results are the same. The approaches may be slightly different from book to book and from what I am going to. Maybe before I start, I should probably give a list of some books, right? Maybe that's not a bad idea, I guess. So Alphos, of course, all of you know. So Alphos' book is a very popular textbook in many places. Alphos is, by the way, one of the great complex analysts of the century. He was, have you heard about the Fields Medal? So the Fields Medal was first awarded in 1936. Alphos was the one who got that. Actually, two people got that in 1936, Alphos and another man. So, of course, because of the World War, the next one was only in 1950. So just to say that your author of your textbooks, not just any author, but the great complex analyst. Finnish, by the way, Finland. He is from Finland. And then, of course, many places also have this as a textbook, Conway, Gamblin. Okay. Sarasan. So all these are available in Indian editions. Okay, Sarasan is in the Trim series, Notes on Complex Functional Theory or something. It's a small book, but a beautiful book. And then there is Raghavan Narasimhan's book also is available in Indian edition, slightly more expensive though, but slightly advanced you can say, but nevertheless it's a very nice book. In some way it is geared towards several complex variables, but it discusses only single complex variables, but the basic flavor comes from several complex variables. Theory of complex functions. Amat is also a well-known complex analyst from Germany. This is also available in Springer Indian edition. But this Ramar's books is not really perhaps suited for to be a textbook, but it's a very, very beautiful book. And it gives lots of historical things, quotations from the original papers and so on and so forth. So, so you must look at some of the other books other than your textbook, right? Of course, first of all, you must look at your textbook, not just your class notes, okay? But other than your textbook, you must just look at some other things, okay? Then only we'll get some, let's say, a broader perspective of the subject. So let's start with the definition of analyticity. The setting is the same. Omega is an open set in the complex plane, right? Let's not write that every time. So f is a function, complex valued function on that. So f is analytic or holomorphic. Holomorphic is usually preferred in the modern treatments. Holomorphic is commonly used in several complex variables, not analytic. If f is differentiable at every point of omega. So here again, there is a remark to be made. The original definition of Cauchy not only assumed that the derivative exists at every point, but also that the derivative is continuous. So original definition of Cauchy was that f has a continuous derivative at every point. So even now you can see some of the books having that definition. All Alphos doesn't assume continuity of the derivative, but I think Conway does assume that f dash is continuous in the definition of analyticity. But it turns out that the continuity assumption on the derivative is superfluous. Okay, it's not needed, it automatically follows actually. So this was shown, proved way back in 1900 by Gursa. The French analyst. So he showed that assumption of continuity of f prime is not needed. It actually follows as a consequence. So that's why it's sometimes called Gursa's theorem or Cauchy-Gursa's theorem. So in view of what we have said in the morning, I mean, it's still morning I suppose, in the earlier lecture. So what are the theorem that we wrote here in the morning? F is complex differentiable at a point if and only if f is real differentiable and Cauchy-Riemann satisfied, so on. So now those conditions, that was at a point. So now same conditions at every point of omega. So f is analytic. So the following are equivalent. F is analytic on omega or in omega. F is real differentiable at each point omega, and the Cauchy-Riemann equations are satisfied. Third condition is that f has continuous first partial derivatives satisfying Cauchy-Riemann equations. See, I will, so our time available is short, so I'll give some of the proofs, I'll not give some of the proofs, I'll sketch some of the proofs and so on, okay? Only then we can, if we start proving everything, we won't end up with anything. Okay, so examples, first of all. Elementary examples. Right? All powers of z. So, in other words, all polynomials. And the usual, the derivative is going to be n times z to the n minus 1 and so on, just like the real case. So all polynomials. So these are all analytic where? Everywhere. Okay? The whole complex plane. Functions which are analytic in the whole of the complex plane are called entire functions. Some of the older books also used the term integral functions. But entire functions was a term used by Weierstrass himself. So 1 over z, for example, where is it differentiable? Except at z equal to 0. Or more generally, 1 over z minus a is differentiable, is analytic on the punctured complex plane. And therefore, rational functions what is a rational function? Have you used the term somewhere? The quotient of two polynomials, right? PQ polynomials. So where is this going to be analytic? Except where the denominator is going to vanish, that means the roots of QZ, right? Set of roots are zeros, as they say. of course, these roots are finite in number. So except for finite number of points, plane with a finite number of holes, it's analytic, right? So these are all obvious points, more or less. But to give more general examples, so let us start by looking at power series. Okay, so that's why the next topic I'm going to discuss is power series. Polynomials are entire functions. Entire functions which are not polynomials, like what? Can you give me another entire function? Of course, we'll come to those things anyway. Exponential function, for example, e power z, or the trigonometric function, sine z, cos z, and so on. Okay, we'll define those things now. That's why I'm going to power series now. So such functions, that is entire functions which are not polynomials, are called transcendental functions. Entire functions. You must have seen transcendental numbers, right? It's like the roots of polynomials. So the exponential function, the trigonometric functions are all examples of transcendental functions. So to look at them, let's look at power series briefly. By the way, just let me mention, having mentioned rational functions, in particular, functions of this type. A, B, C, D can be, of course, complex numbers, or real number, doesn't matter. So where is it going to be analytic? Except when the denominator is 0 or z equal to something, minus d by c or something, right? So there's just one point where it's not analytic. So these are some simple kind of functions, but they play important roles in many situations. So these have a name. They are called linear fractional transformations. Linear means functions of the form az plus b. So linear fractional, so both numerator and denominator are linear functions. They are also called Mobius functions. Mobius, you must have heard of name Mobius in some other context. Mobius band, for example. In number theory, we'll say something about this later probably, at least some special Mobius functions. Okay, so let's look at power series. What is a power series? A series of the form n z minus z naught to the power n 0 to infinity is called a power series around z naught. Orbit center z naught. Of course, as it is just a formal series, we have to look at when it converges and so on and so forth. Convergence problems have to be addressed. Look at power series around 0. So series of the form, it doesn't make a difference as far as results go. just have to translate. The writing becomes a little simpler. So you don't have to write Z naught every time. So the basic facts about power series. So first of all, it can happen that, of course, obviously when Z equal to Z naught is going to be 0. Everything is 0. Except, of course, the constant. A0 is going to be there. So at Z equal to Z naught, the series always converges. Right? But it can happen that it doesn't converge anywhere else. Right? It can happen that a series converges only at Z equal to Z naught. Right? Or it can happen that it converges everywhere. So first of all, we have to look at where the series converges and where it doesn't. Okay? So the first result, the basic result about power series is the following. Going back to again Cauchy and Abel, so on. So let us, just for simplicity, as I said, we'll look at this power series around 0. Suppose this converges at some Z naught is not equal to 0. Of course, at 0 it always converges. Suppose it converges at some non-zero point. Then what can you say? So take any smaller disk. So suppose any point on the smaller disk there. So what happens at Z1? So the assumption is that this converges. At Z equal to Z naught, you have convergence by assumption. So this implies in particular the nth term of a convergent series goes to 0. Right? So and then goes to infinity. Z naught, yeah. In particular, it is bounded. Right? Any convergence sequence is bounded. What are we interested in at Z1? So we want to look at so suppose this is R, okay, Z1 is somewhere here. So what is R? No, not this, but let's take what we need is this mod Z1 over mod Z0. So mod Z1 is less than mod Z0. So this is strictly less than 1. Let's say this is R. So now we can write this as So this is going to be less than or equal to this part less than or equal to m. So this part is r, m, r power n, where r is less than 1. So what is called the Weierstrass m test, right? The nth term is dominated by constant times. So r is less than 1, so you know that this is convergent, right? It's a positive real number less than 1, 1 over 1 by 1 minus r. Okay, so that this series converges absolutely and uniformly on this disk, right? On any smaller disk, right? Okay, smaller means smaller than this disk. So let us look at, so define either you can state it either way, where this converges or where it's bounded. This sequence is bounded, right? That means this less than or equal to constant independent of n. Or you can also take supremum of all mod z, where sigma a and z n converges. So the result is that sigma a n z n converges for all mod z in mod z less than r. Does not converge for so we have of course r can be 0 or r can be infinity. Of course, the picture is for the case when r is non-zero and finite. So it converges everywhere inside this circle, does not converge anywhere outside the circle. Okay? But it doesn't say anything about what happens on the circle. It can happen that at some points on the boundary it can converge, at some other point it may not converge. So nothing is said about the boundary behavior. So R is called the radius of convergence of the power series, and this is called the circle of convergence. So nothing is said about convergence or otherwise for points on the circle of convergence. Of course, R can be infinity or R can be 0, as I said. The basic formula for calculating this R is the well-known formula. Lim sup of mod a n power 1 by n. So if the lim sup is 0, then the radius of convergence is infinity. If it is infinity, radius of convergence is 0. This formula was given by Cauchy in 1821, but it was again rediscovered by Hadamard in 1892. Jacques Hadamard was a French mathematician at the turn of the 19th and the 20th centuries. Was one of the, let's say, profoundly influential in the sense of development of mathematics, development of analysis in particular, in that later part of the 19th century and the early part of the 20th century. He was famous for, among other things, of course, I don't know, there is a Hadamard's factorization theorem for entire functions, which I don't know whether you have in your syllabus or not. There is what is called the Hadamard three circles theorem and so on. But one of the most famous results of Hadamard was the proof of the prime number theorem. In 1896, he gave a proof of the prime number theorem. Of course, there was another person who also gave a proof at the same time, Poussin called. Anyway, so this formula is useful in computing the radius of convergence of power series. Okay, let's give some quick examples, not too many, but the basic. This is the exponential series, so the radius of convergence is infinite in this case. This is geometric series, 1 by 1 minus z. By the way, the series, the circle of convergence is the unit circle, right? At z equal to 1 does not converge on the unit circle. Let's see, and then or n power n to z power n if you want. Here the radius of convergence is 0. course, this is the first one, of course, is the important exponential function, which will come to soon. But first, let us say something about the function defined by the power series. So, if inside the radius of inside the circle of convergence, this series converges, right? So, it gives you a function. So, what can we say about that function? So, the basic facts about power series. So, before that, let's remark that using the Hadamard formula, okay, so state the theorem after that. So, you have this series. So, by the way, so whatever you have said for this series is true for power series around any point. Just written down for z equal to z naught equal to 0. So, n z minus z naught power n, everything is. You look at the series got by differentiating these terms here. Differentiate every term. N, an, z to the n minus 1. Of course, n equal to 0 also you can write, doesn't matter because it goes off anyway. What about this? If R is the radius of convergence of this series, this also has radius of convergence R, if you use the formula here. Okay? N power 1 by n goes to 1. Right? Limit of n power 1 by n is 1. So you will have, if you put an n there, so that will become 1. So you will get R itself back. I mean, you can repeat this. You can repeat any number, you can differentiate each term any number of times, you still get the same radius of convergence. What is the next one? N into n minus 1, an, that to the n minus 2. Again, radius of convergence is R and so on. So, by differentiating each term, you don't alter the radius of convergence of the power series. Okay, so keep this in mind. So R is the radius of convergence. Of so this defines a function okay, so for mod z less than r, this series converges, so denote the sum by f of z. So this gives you a function f defined on that disk mod z less than r. Then f is analytic and the derivative is given by term-wise differentiation. So you can get the derivative by just differentiating each term of the series. We already observed that this differentiated series also has the same radius of convergence, and therefore this makes sense. So this defines a function on that, and that function is actually the derivative of f. let us try to quickly look at the proof of this. So fix A, mod A less than R. So we have to show that f prime A exists. So to show and is equal to or call it Z0 instead of A if you want, doesn't matter. Okay, so the right call that function as G. So we have to say that f prime A exists and is equal to G of A. So let us start. Right, we have to show that this goes to 0. Fz is this, so okay. You can factorize this, z minus a into something. So we can cancel off that z minus a with this. So you're going to get what? Sigma that right? No. N, you have to get n minus 1. So, minus 1. Right? Z to the n minus 1 plus z into, z to the n minus 2 into A and so on. Is it okay? Have I written correctly? Minus this same thing. So take the sum outside. So n times an, a to the n minus 1. So combine this with this. So you're going to get sigma an maybe I could have written it the other way. Because you have powers per A here. So let me write the other way. It doesn't matter though, but see, I have one an a to the n minus 1. There are n terms like this. So I have taken 1 for each of these n terms here. In the sum there are n terms. So let us estimate this. Check whether I have not made any mistake there. Look at this. Z to the k minus a to the k. Again you can write it as z minus a into k minus 1, etc. a to the k minus 1. K terms here. So when you take absolute value, So each of these is less than r, modulus, in modulus, each of these is less than r. So there are how many terms? N minus 1 terms. So n minus 1 r to the n minus r to the k minus 1, right? How many terms are here? There are, we will come to this sum. We are looking only at this now. So k terms are there. K, r, k minus 1. Or let's say mod z. Let us take some, call this, both are less than r, less than capital R, let's say. So we are looking at a smaller disk around A. So k times r to the k minus 1 times mod z minus A. So if you plug in here, you are going to get the whole thing modulus of this so this is again less than r. So there are okay, so what do we get here? K goes off, r to the n minus 2. So sigma 0 to n minus 1, k. So that is n into n minus 1 into, what is that? N into n minus 1 by 2, correct? So 0 to n minus 1, k. 1 plus 2 plus up to n minus 1. This whole thing is convergent because we already have shown that, observed that this is convergent for all mod z less than r. So this is some constant, okay? So this is c times mod z minus a. So as z goes to a, it goes to 0, so the left hand side goes to 0. So anyway, the conclusion is that the function given by a power series defines an analytic function inside the circle of convergence. So this is true, you see, for not only for f dash is also analytic because it has the same radius of convergence. So inside that circle, f is analytic, f dash is also analytic, and so on. all the successive derivatives of f will be analytic functions on. So f and all its derivatives are analytic in okay, I'll just stop by saying or defining exponential function. We already observed that the radius of convergence is infinite. So this gives you a function which is analytic in the whole plane. So this is an entire function. And so are the sine and the cosine functions. How is sine defined? How do you define sine and cosine in terms of the exponential? You remember Euler's formula? E power ix is equal to cos x plus I sine x. So e power minus ix is cos x minus I sine x. So we add, we are going to get twice cos x. So cos x is e power ix plus e power minus x ix by 2. So you take that as a definition here for complex thing. Okay? And of course, Euler's formula will be consequence of that. Hindsight. So this by definition is cos is e power iz plus e power minus iz over 2. This is going to be to I. These are the definitions, okay? For complex z, you define sine and cosine by this series. Of course, you can write down the series now, right? What is the cosine series? Only the even terms will occur. Minus 1 to the n. No, 2n somewhere. 2n, right? Here. 2n factorial. 1 minus z square by 2 factorial. Is it okay? 2n factorial, yeah. Not 2 into n factorial. Similarly, the sine function will give you only the odd terms there. N equal to 1 to infinity. Is that okay? No. You start with z, right? Yeah, that's okay, right? So this is fine. 1. So these are examples of entire functions. Yeah. So of course the quotient function, the tangent function, tan z will have will not be analytic at all points. Points where cosine function is 0, there will be problems. This is an example of what are called meromorphic functions. functions. We'll come to these things later.